So we are back again with the chapter 2 of the differential equation, which is all about the solution of some first order first degree. So this is Engineer Jana May Domingo from Summer State University College of Engineering. So we are in the second chapter of the differential equation, and the topics include the variable separable, the homogeneous, exact, linear, equation linear in a function, and the Bernoullis. So we are now in the last topic of this chapter, which is all about the Bernoullis equation. So 2.6 Bernoullis equation. Defining Bernoullis equation. So this is a first order differential equation that can be written into this form. So this form is read as the derivative of y with respect to x plus function p times y is equal to function x times y raised to n, where function p and function q are continuous on an interval a, b, and n is a real number. So these are the steps on solving Bernoullis differential equation. First, we need to rewrite the differential equation into this form. Now, if we cannot change the equation into this form, and then we can say that that is not a Bernoullis differential equation. So do not proceed in the next steps if you prove that that is not a Bernoullis differential equation. First, we need to apply that z is equal to y raised to 1 minus n. And then, we differentiate this substitution with respect to x. So differentiating, we will get this equation. So we will get this equation. And we can express this in terms of dy over dx. So expressing it in dy over dx, we will have this equation. So our dy over dx is equal to the quantity of 1 over 1 minus n times y raised to n dz over dx. And then, we now substitute this equation to the differential equation. Hence, the differential equation, the Bernoullis differential equation, changes into this form. So it becomes like this. And then, simplifying the equation, that gives us this equation that dz over dx plus the quantity of 1 minus n times the function p y raised to 1 minus n is equal to 1 minus n qx. So we know that y raised to 1 minus n is equal to z, and that gives us the next equation. So this equation becomes the new px, and these equations become the new qx. Instead of using just qx, this will be our qx, while this will be our px. And then substituting that y raised to 1 minus n is equal to z, that gives us this equation, and observing, this could be solved using the linear equation. So we can proceed in solving through linear equation. But this equation is in terms of z, right? So instead of using y, we use the variable z. So in the solution of Bernoullis equation, after integral mathematical operation in the equation, we can actually use the linear equation for solving the problem. So this is the equation used in solving for the general solution of the linear equation, where our z is also equal to y raised to 1 minus n. So we can also say that the general solution for the Bernoullis equation is given by this equation. So for example, we have this equation. So dy plus y dx over x is equal to 3x squared y squared dx. So our first step in solving for the given example is to change that into the standard form of Bernoullis equation. So by observing the values, we can actually change it into a Bernoullis equation through dividing the whole equation with dx. And that gives us this equation. So dy over dx plus 1 over xy is equal to 3x squared y squared, where 1 over x represent our px, and the qx is equal to 3x squared. And the n is 2. So our n should not be equal to 0 or 1. Please remember that. And then for the utilization of Bernoullis equation, the actual px and qx that we will be using is not the px and qx we have found in the equation, but they are used to solve for the actual px and qx that we will be using. So our actual px and qx, our actual px is actually equal to 1 minus n times the px. So that px is the 1 over x, and the qx is equal to 1 minus n qx, and that qx here is actually equal to this qx. So solving, the actual px to be used is negative 1 over x, and the actual qx to be used is the negative 3x squared. So the next step now is to reduce the differential equation into this form. So in this form, the 1 minus n px is actually our new px, and the 1 minus n qx is our new qx. So substituting the values we have solved, we have this equation, and simplifying, that will give us that dz over dx minus z over x is equal to negative 3x squared. Observing the given equation, the linear equation method can be utilized to solve for general equation. But as we can see, instead of y, we have the variable z. But later on, it should be substituted by its original value, which is y raised to 1 minus n. And now we can solve for the general solution of the equation. So this is the equation to be solved using the linear equation now, where the 1 over x is our px and the negative 3x squared is our qx. So we will be using this formula and solving for the integrating factor, that is equal to x raised to negative 1. So the solution is at your screen. So just the same steps on how to solve the integrating factor in the linear. This is still the same. And then substituting the values, we have the n is equal to 2 and 1 minus n is equal to negative 1. So substituting the values, we will have this equation. And then that is also equal to this equation. So we factor out the negative 3 since it is constant. And then we have to integrate the x dx, and that gives us that x raised to negative 1z is equal to negative 3 times the quantity of x squared over 2 plus c. And that is also equal to x raised to negative 1z is equal to negative 3 halves x squared plus c. So this equation still can be simplified because we have z is equal to y raised to 1 minus n, which is the original value for the z, wherein our n is equal to 2, so that gives us our y is equal to negative 1. So substituting the values, we will have this equation, and that will give us the general solution that 1 over xy is equal to negative 3 halves x squared plus c. And my reference book is the Perante and Gumba 2014 Differential Equation 2nd Edition Work Textbook. So thank you for listening. Have a nice day.